Good morning to Nordin. My name is SHIM with matching number 216913. And now I would like to present my assignment 1, which is Fundamental Principle of First Law and Second Law of Thermodynamics. And here is the content that I would like to present today. For the first law of thermodynamics, it states the conservation of energy principles, which means that the energy will only can be changed its form to another, but cannot be destroyed or be created under any circumstance. So for this law, it's come out an equation which is total energy input plus total energy output equal to the change of total energy in a system. So the change of energy in a system is equal to the heat transfer minus with the work done. And the total of change in the total energy change in the system also equal to the total energy change in three types of energy, which include internal energy, potential energy, and kinetic energy. And the equation to calculate these three energy are listed below. So now I will present the equation to calculate the energy. For the first one is the total energy. And as I said just now, total energy is equal to the sum of internal energy, potential energy, and kinetic energy. And the second one is about the enthalpy. Because in the opposite case, we will usually use the enthalpy instead of internal energy. So it's important to know how to calculate enthalpy. So yeah, the change in enthalpy is equal to the change in internal energy times with work done. Plus work done. Yeah, the pressure times with the change in volume is equal to work done. So the third one is about the work, and we have three types of work here, which is work done, electrical work, and shaft work. And work done equal to pressure times with change in volume, and the electrical work equal to voltage times with number of column, and the shaft works is equal to 2 pi number of revolution times with torque. To know, for your information, the internal energy, which is U, is usually used in the closed system. And yeah, as I said just now, the enthalpy hash is usually used in open system. Energy conversion efficiency. Efficiency is the fraction of desired outcome to the required input for a device. So as the equation that I show here, efficiency equal to the desired output divided by the required input. So if we want to calculate the overall efficiency, which include some or a few more than two device, that we can just times the efficiency of all the device together. Then we can get the overall efficiency. So and here I put an example, which is water heater. The desired output of a water heater is heat, yeah, and the required input is electrical energy, so that the water heater is able to convert the electrical energy to the heat, to the water, to heat up the water. So yeah, the way we calculate the efficiency here is equal to the amount of heat delivered to the water divided by the amount of electrical energy supplied to the water heater. So here is the application for closed system and open system. For the closed system, as I said just now, we will usually use the internal energy. And for the open system, we will usually use the enthalpy. Here is the application for open system. To ease our calculation, usually we will make some assumption in our calculation, usually, especially for open system. There is a few magnitude that we will assume is equal to zero. So here is the assumption we will consider it to make based on the question and based on the device that we get. And in our syllabus, we will usually encounter 6 type of device, open system device here, which is nozzle and diffuser, turbine and compressor, trimming valve, mixing chamber, heat exchanger, and pipe and duct flow. So now we turn to the second law of thermodynamics. This law explains the heat conversion and the flowing direction. It also states the impossibility of 100% efficiency of heat engine. So in this law, it has two statements. The first one is Kelvin plus statement, and the second one is Clausius statement. So now I will introduce what is heat engine. Heat engine is a device that is convert pressure of heat to the work. So they will receive the heat from a high temperature source, and they will convert them, pressure of them, to the work. And they will reject the residual heat waste and the low temperature sink. And here is the equation to calculate the thermal efficiency. Thermal efficiency equal to the net work output divided by the total heat input. For the Kelvin plug statement, it states the impossibility of 100% conversion of heat to work because we know that it's impossible to have 100% efficiency of heat engine, and heat engine will only convert the partial heat to work. So yeah, this is why the Kelvin plug statement state the impossibility of 100 conversion. So here is a diagram that shows a heat engine that violates the Kelvin plug statement because based on the Kelvin plug statement, it's impossible the heat input equal to the work net output. So now I will introduce the coefficient of performance. It usually let us know the efficiency of or the performance of refrigerator and heat pump. Refrigerator is the device that aims to transfer the heat from low temperature to high temperature, while the heat pump is aimed to absorb the amount of heat from low temperature to high temperature. Although their function is similar, but its aim is different and their desired output is different. As we can see here, the desired output of refrigerator is the heat from low temperature, but the desired output of heat pump is the heat from high temperature. So their equation will be different. But we can conclude that the COP of refrigerator is equal to the heat from low temperature divided by the work net input, while the COP of heat pump is equal to the heat from high temperature divided by the work net input. So finally, we can make a short summary. COP heat pump is equal to the COP refrigerator plus 1. So now we turn to the second statement in the second law of thermodynamics, which is Cauchy statement. Cauchy statement state the possibility of transferring heat from a cold media to a hot one by using external device. Because before this, what we learned is heat flows from a hot one to a cold one. But in this statement, it state the possibility of opposite flow direction of heat. So, and here is the diagram that shows a refrigerator that violate the Cauchy statement because this refrigerator transfer heat from low temperature to high temperature without an external device. So the refrigerator needs a compressor that is driven by an external power source to operate so that the work done consume will contribute to the heat removal from a cold body to a warm one. So now I will introduce reversible process and irreversible process. Reversible process is a process that able to turn back to its initial state without leaving any trace on the surrounding, and is a ideal process that is impossible occur in the real life. And on the other hand, the irreversible process is a real process that could not return to its initial state due to some natural resistance. For a reversible system, there is a Carnot circus to demo a whole reversible circus. So first thing, it will undergo a reversible isothermal expansion, which means the volume will increase and there is a heat absorbed to the system. And next, it will undergo a reversible adiabatic expansion, which means the volume will increase, but there is no heat transfer on that. And next will be reversible isothermal compression, which means the heat will release from the system to the surrounding and the volume will decrease. And the last one is reversible adiabatic compression. The volume will decrease and there is no heat transfer on that. According to the Carnot principles, the efficiency of a reversible heat engine is always higher than irreversible one. So, and the second point is the efficiency of all reversible heat engine is always the same under the same condition. So for the first one is the heat engine. The first equation is the equation to calculate the efficiency of irreversible heat engine. And the second equation is the equation to calculate the efficiency of reversible heat engine. And then we can conclude the efficiency of reversible heat engine is higher than the efficiency of real, which is irreversible heat engine. And same goes to the second one, the for the refrigerator and heat pump. And we can conclude that the COP of reversible is always higher than the irreversible COP. That's all for me. Thank you for listening.